Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Zafran bin Wayan Zailani. My metric ID is MA22146 and my group members are Muhammad Yusof bin Kamarul Faizal MH22011 and Muhammad Radi bin Muhammad Nizam MH22013. We are from group 5 and today we will present our group project titled Electric Vehicle Battery State of Health Estimation using Machine Learning. And this project focuses on applying artificial intelligence technique to improve the battery health monitoring in electric vehicle. Okay, for our introduction, the adoption of electric vehicle has increased rapidly in recent years. So, lithium-ion batteries are the main energy source for EVs, and their degradation directly affects the driving range, safety, and maintenance costs. Therefore, accurate battery health monitoring is essential for reliable EV operations. Okay, next is our problem statements and research objective. So, for our problem statement, battery degradation is a complex and non-linear process influenced by many factors. So, traditional models struggle with accuracy and scalability. Therefore, our objective is to estimate the battery state of health using machine learning model and compare their performance for engineering applications. Okay, next for our literature review. Previous studies show that state of health is one of the most important indicators for battery aging. While physics-based models are interpretable, they are complex and sensitive to noise. So, recent research highlight that machine learning, especially assembled models such as XGBoost, provides better accuracy. So, optimization techniques like particle swarm optimization further enhance model performance.
This slide describes the methodology used for data equation and pre-processing in this study. The battery data were obtained from the NASA prognostic battery dataset of model B5, which consists of 168 charge-discharge cycles conducted under the room temperature conditions. This dataset is widely recognized and provides reliable information for analyzing battery degradation and state of health (SOH) behavior. In this study, battery capacity measured in ampere hours is selected as the target variable as capacity fade directly reflects battery aging. The cycle number is used as the input feature to represent the progression of usage over time. As shown in the figure, there is a clear and gradual decline in capacity with increasing cycle number, confirming the consistent degradation trends. Priority to model development, the dataset was divided into 80% training data and 20% testing data to ensure unbiased performance evaluation. Additionally, standard scaling was applied to normalize the data, enhancing the numerical stability and improving the robustness of the modern machine learning models. Overall, this step ensures that the dataset is clean, structured, and suitable for accurate battery state of health prediction. This slide presents the baseline model used for battery state of health SOH prediction. Two benchmark models were selected, which is linear regression and k-nearest neighbor (KNN) regressor. This model serves as the reference points for evaluating more advanced prediction methods. Linear regression models as a simple linear relationship between cycle number and battery capacity. It is computationally efficient and easy to interpret, but has a limited capability in capturing nonlinear degradation trends. The KNN regressor predicts the capacity based on nearby historical data points, although more flexible. It is sensitive to noise and outliers. As shown in the tables, the linear regression achieved a lower RMCE of 0.0341 compared to 0.0649 for Can-N. Both models exhibit negative R-square values indicating limited predictive performance. This result highlights the limitation of baseline models and motivate the use of advanced machine learning approach. This slide presents the baseline model used for battery state of health SOH prediction. Two benchmark models were selected, which is linear regression and k-nearest neighbor (KNN) regressor. These models serve as the reference points for evaluating more advanced prediction methods. Linear regression models as a simple linear relationship between cycle number and battery capacity. It is computationally efficient and easy to interpret, but has a limited capability in capturing nonlinear degradation trends. The KNN regressor predicts the capacity based on nearby historical data points. Although more flexible, it is sensitive to noise and outliers. As shown in the tables, the linear regression achieved a lower RMCE of 0.0341 compared to 0.0649 for Can-N. Both models exhibit negative R-square values indicating limited predictive performance. This result highlights the limitation of baseline models and motivate the use of advanced machine learning approach.
Alright, moving on the result, we measure performance using RSME where a lower numbers means better accuracy. Surprisingly, in the specific experiment run, the linear regression baseline actually achieved the lowest error, followed by our optimized XGBoost with KNN performing the worst. So this graph visualize why we got this number. The black line is the real battery health. The green line follow the trend smoothly. Our advanced model try to learn the complex pattern, but because the test data happen to follow the straight drop, the simpler model won the specific round. However, the XGBoost model successfully outperformed the KNN. Alright, for discussion and engineering side, from the for the engineering perspective, this teaches us the valuable lesson. Complexity doesn't always equal accuracy if the data is simple. However, we successfully proved that the particle swarm optimization worked. It automatically turned our AI into a real-world scenario where the battery health fluctuated widely due to the temperature of driving style. Our advanced model would likely be more robust than a simpler linear line. In conclusion, we successfully developed a framework for predicting battery health. While linear regression held out well on the specific dataset, we established on the working XGBoost pipeline that can be scaled out for more complex EV data in the future. That concludes our presentation. That's all of us for the presentation. Thank you.